And we're live. Hi, everyone. I'm Hugo Bowne-Anderson here from Coiled, where we're liberating everyone to use Dask and the Python ecosystem to scale their data science and analytics and machine learning and whatever AI is stuff to the cloud. I am so excited to be here with Chelle Gentemann from the Farallon Institute, but also from being an awesome human. Hi, Chelle.
Hey, how you doing, Hugo?
I'm well. And we are live. I can hear myself. I would love everyone to introduce themselves in the chat. Let us know who you are, what you're up to, what your interest in Dask, and what we're talking about today is. And while you're doing that, perhaps, Chelle, you could introduce yourself in several words, or more than several.
Yeah, no problem. I prepared a few slides for this, so I'll share my screen.
Yeah. Let's jump in.
How's that?
That's great. That's you.
Great. So I am Dr. Chelle Gentemann. I'm an oceanographer, and I specialize in data taken by NASA satellites, also NOAA satellites, and taking that information and producing maps like the one above, which is a sea surface temperature, so an ocean temperature anomaly. This is during the Pacific warm blob, where temperatures were almost 4 degrees warmer than normal in the Pacific Ocean. Australia is now having a marine heat wave right now, and they keep popping up all around the world. So we're very interested in what the ocean's doing and how it's impacting weather and climate. So I work a lot on ocean temperatures and measuring them from space. I also work with robotic sailing vehicles, which are called sail drones. I've had cruises go every year up to the Arctic and also down in Barbados. My kids are still upset that I did not get to go on a cruise to Barbados. And so in the Arctic, these robotic sailboats go up and they collect all sorts of air-sea interface data. And we use those in our algorithm development for the satellites. I'm also the lead scientist on a new proposal to NASA for a new NASA mission called Butterfly. And this is a picture of our spacecraft and instrument, so the whole observatory down below. And it's a passive microwave radiometer with a high frequency antenna, low frequency antenna to measure the air-sea interface, the fluxes at the air-sea interface. And that's who I am and what I do.
Fantastic. Thank you, Chelle. And once again, congratulations on getting the proposal in. I know that was, to understate it, a huge amount of work for you. So that's fantastic.
It's interesting working on really big projects like this. I think it's probably what Matt felt when he started Coiled, and what anybody who starts something, you start something and you get yourself in deep enough that it's too late to turn back.
I think it's how we all feel every day at Coiled, but
yeah.
that may be a different story. This is cool. We've got Guy Maskell tuning in from England. We've got Pavitra from India. We have David from France. You're on the west coast of the US. I'm in Sydney, Australia. So it is truly, we are going around the globe together today, which is exciting and timely. People who are just joining, please introduce yourself in the chat. Let us know what your interest in what we're chatting about today is, and your interest in Python and Dask. And if you can let us know where you work, that'd be great as well to get a bit more context. I'm going to say something slightly tangential. You mentioned, Chelle, that your children would have been happier if you'd figured out a way to get to Barbados. Okay. So I actually went to Barbados several years ago, and it was when I was applying for a visa for a job in the US. And I was living in New York and I was taking a new job, and it was in February. And the immigration lawyer my company was working with, my CEO wanted me to start ASAP, and the immigration lawyer said, look, you can't start ASAP. You need to leave the country to get a visa, and you probably need to go somewhere for 2 to 3 weeks. And he said, usually I'd say Canada. And I was like, Canada in February? And he was like,
no.
And he said, actually, the quickest processing times at the moment are in Barbados. So he sent my boss an email saying, Hugo can't work and has to go to Barbados for 2 to 3 weeks for you to be able to employ him. And my CEO sent me an email pretty much saying, using a bunch of expletive, saying, is this guy for real? Like, what what on earth is happening here, man? And I was like, hey, it's what the lawyer says. So he's the professional. And I had a lovely time there.
Yeah, it seems beautiful. So I've heard.
We have someone tuning in from Maine. We have Sammy from Canada and Marcos from Argentina. So there's a lot of people in the room, which is it's great to see you all. For those of you who are joining us for the first time, definitely hit subscribe and check us out at Code HQ on Twitter if you enjoy the stream and want to check out more. But I thought I'd just say a bit more. And this is actually in the description on YouTube. But one of the things I love about our conversation, Chelle, is how much your focus is on open, inclusive, and interdisciplinary science, and using cloud compute, but thinking about opening up science more generally. One of the first conversations we had, you told me about how fundamental you thought Dask and the Python ecosystem was to opening up. Let me say, we're actually in science, among other places, where there's a huge skills gap, and we're actually in a skills crisis. And you didn't frame it necessarily like that to me, but you professed how Python and Dask really helping to meet the needs of working scientists today. Having proper incentive systems that give them the time and bandwidth to learn these skills is a very different question. But I think maybe it would be great if you could just tell us a bit about how you got introduced to Python and then the power of Dask for you. And then we can jump into your slides and notebooks.
Yeah, I got introduced to Python when I moved from a commercial company, and I lost access to about 18 years of research code. It was all in Fortran and MATLAB, so it's not that big of a loss. But I had this opportunity. I had a fork in the road, and I could either start again, just reinventing what I knew I had already written in Fortran and MATLAB, or try to explore something new and different. And I decided to try Python. I'd been hearing a lot about it for scientific computing. I hadn't quite connected it to cloud computing yet and how it would increase my accessibility to that. And so when I first started learning Python, I didn't really understand the open ecosystem and the open source library ecosystem. So I was just using basic Python, and it was essentially Fortran code written in Python. And what I mean by that is it was like lots of indices and loops, and it was so slow. And then as I slowly started to understand, like, okay, you have to use pandas and NumPy, and then once you find out about Xarray, and Xarray was really the first time that when I started using Python, I said, oh my gosh, this is game changing. And the part about Xarray that just really called to me was the integration with Dask, because all of a sudden I could create workflows and I could create pipelines that didn't require me to constantly be inputting and then outputting temporary files, keeping track of those files in order to do the next step in my science or my analysis. I could create workflows that could be entirely done on the fly, and it was lazy loading and not having to really worry about how much RAM I had and worry about all of the little details about what my programs were going to do to the computer I was working on. And that, I'm an oceanographer, so my programming classes consisted of one class in Lisp in about 1991, and that is my entire training in computer software analysis. Wow. And so everything else, and I think many scientists are in the same boat. You pick it up as you go, and with Fortran, you're really forced, the libraries for Fortran are so minimal, and you end up just emailing code around and trying to share things, that being introduced to the Python ecosystem was just completely game changing, because all of a sudden things that I had spent, if you wanted to do a Weibull function, you could either pay MATLAB for a library that had the Weibull function built in, or you could write your own. And it was just frustrating, now it feels like everyone is working together to build a new ecosystem that we can all work in and just advance so much more rapidly that like every day I'm doing science and I'm just blown away with the tools that I have access to.
Fantastic. So that seems like an amazing point to dive into what you're thinking about here and what you're working on.
Yeah, so I thought it might be interesting because Hugo and I have talked a lot about Dask and Python, but I thought it might be interesting to sort of explain how oceanographers why an oceanographer needs to code. And I work a lot in ocean temperature. So from space, this is a picture of the Aqua satellite at the top. On the Aqua satellite, there's a microwave radiometer on the front of the satellite. This antenna actually spins completely 360 degrees every 1.5 seconds. And it images the Earth as it does so. On the bottom of Aqua is another instrument called MODIS, which also measures ocean temperature, but using infrared frequencies rather than microwave. And below this is GOES. So the Aqua satellite, this is about $1 billion investment. The GOES satellite below is about a $2.5 billion investment. This is a NOAA satellite. This sits in a different orbit and it has an imager on it that also measures ocean temperature as well as clouds and lots of other parameters. When we're talking about ocean temperature, this is a close-up of the Gulf Stream. And the Gulf Stream runs up the west coast of the United States, and as it starts to separate, it becomes unstable and it has lots of fluctuations like eddies in it that we call in the ocean. And these affect our weather, they affect our climate. The ocean really starts to impact how we live our lives through weather and climate. And that's why a lot of people are interested in studying it. So it's a key measurement. If you want to know weather, you need to know ocean temperature. It's the bottom boundary condition in all of the weather models. You also want to understand extreme events. Again, you want to understand what's happening off the coastline. So these are some of these examples of these heat waves where we've had record Arctic temperatures. We've had record temperatures along the West Coast and drought. And a lot of this is related to these really warm ocean temperatures that we've been seeing in the Pacific Ocean. We also have, this is an image. So here's Baja coming down. And this I thought was just a nice image because it shows you some of the variability that we see in the ocean temperatures. It's not just one temperature, and these affect local weather, they affect fisheries. So this is really important for a lot of people, and it's measured from space, but how do we sort of do this? So
and I just want to say those temperatures were in Kelvin, is that right?
Yeah, some of them, it depends on how they're stored. These are stored in Kelvin. The CF convention is that they're always stored in Kelvin.
Makes sense. Cool.
A lot of people think about them in Celsius or Fahrenheit, depending on what country you're from.
Yeah.
Yeah, so these sort of maps are produced by essentially every operational agency in the world. So the UK Met Office, IFREMER in France, DMI, the Danish Meteorological Institute, Australian Bureau of Meteorology, the Japanese Meteorological Agency, the Canadian Meteorological Agency, the US, Navy, NOAA, NASA, and also just a lot of scientists. They're producing a gap-free, what I mean is like an interpolated daily ocean temperature map. And these are used for science, industry, operational, weather prediction, and climate. And this is a really poor resolution image, so I apologize. And we're doing this, there's like a whole lot of satellites up there that are taking ocean temperatures. And how do we get all of this data? It went from maybe 20 years ago where we had just a couple of satellites up, and we were at a position where if one satellite had a gap, we would just have to take that day of data and just make it keep going until we got the data back in place.
And who owns all these satellites?
So these are run by, there's ESA, EUMETSAT, NASA, NOAA, JAXA, the Chinese Space Agency. I'm looking over to
So
see
they're
if
all
I'm
governmental
India.
organizations.
Yeah, they're all government, either meteorological or space agency.
Great. And there's some sort of, this may be a
Agreement.
naive question. Yeah, agreement to share the fruits of, share the data, essentially.
Yeah, so almost all of them, with some exceptions, but most space agencies have embraced open data. And that movement started about 20 years ago. And I think maybe even a little bit longer than that. And because we all share our data openly now, we are in this position where we can start to make really high resolution daily maps of ocean temperature. And it's not just true for ocean temperature. Almost all the data, NASA has an open data policy. NOAA has an open data policy, ESA, EUMETSAT. So everyone is sharing their data. That's
Great.
easy to say, but how you share your data is also important, right?
Can you say a bit more about that?
So one of the projects that I've been part of for about 20 years is called GRIST. It's the Group for High Resolution Sea Surface Temperatures. When we started the group, every space agency shared the data from a FTP site that you had to know about. And sometimes you had to have a password to get onto. And every single instrument had a different data format. So there was no standardization at that point. NetCDF was just a twinkle in the eye, which is a data format that's really common now in earth sciences. Most people were sharing their data in just flat binary files. So you had to know how, you had to have the key. You had to know how to read the files. And then HDF came along, and then NetCDF, these two file formats that were more sophisticated and included metadata and coordinate systems. And so we basically, all of the ocean temperature people got together and said, okay, we're going to just define a format and everybody's going to follow it so that I can read a data set from any one of these satellites with one call, with one program that understands how to read all the data. And that was another game changer.
That makes sense. And I do think open data is one thing, and you can have open data, but having it actually usable or practically open. Yeah, exactly. I remember when I moved to the US and I was living in New York, like New York City had opened their data, whatever that means, right? And I went in to try and play around with it, and there was no metadata. It wasn't even clear what the columns were. And I was like, this is not, like, it is open, quote unquote, open data in some sense, but it isn't practically open or accessible, as you said.
And then you get into, like, is it big endian, little endian? Like, what are the bit orders?
Yep.
And some machines put a byte right at the beginning of writing out arrays. Other ones don't. Like, it was just a mess before these standardized formats came out. And so the standardized formats, HDF and NetCDF, really were game changing for scientists, I think, in order to be able to share data and understand its quality and be able to trust it. So
with that, maybe we should jump in. Oh no, I also wanted to say I'm slightly concerned in your previous slide. It looks like Earth is on fire, but that's just a matter of the scale and the visualization, presumably.
Yeah, so this is a really interesting current. If you look in the upper right-hand corner, you can see sort of lower Mexico and part of Central America. And then South America is on the far right-hand side. So this is a map of the equatorial Pacific Ocean. And in the equatorial Pacific, you get the equatorial current, and you get these tropical instability waves is what they're called. And you get these waves moving along the currents. And they actually change the wind patterns, they change the rainfall, and they actually map into the upper atmosphere and affect weather. So it's really interesting. But yeah, it's just a color.
Fascinating. Thanks, Chelle.
Yeah, so I'll skip this. I was just going to say, the satellites are all in different orbits. There's 3 primary orbits that the satellites go into. And when you get the data, you get a map like this. And there's a lot of missing data, and different instruments are missing different data for different reasons.
I can see a bunch missing in diagonal strips for some reason. That's where my foot, and then some blobs.
So the strips are because if you have over here on the right, if you have a polar orbiter, the polar orbiting satellite just goes around the Earth. Normally they're sun synchronous, and the Earth rotates underneath them. And so if you imagine a satellite coming along here, it takes a strip of data, goes down on the other side, the Earth moves, and then it takes another strip of data, the Earth is moving, and another strip of data, and you end up with an image like this.
Ah, cool.
Isn't that cool?
That's really cool.
Some instruments measure a wide enough area that you don't see these strips, but for most instruments, you do see the strips. And then the other missing data, this is an infrared ocean temperature, so those are clouds. And then of course you can't measure under the sea ice, so the sea ice areas are missing. And each type of data set has different reasons that data are missing. But if you want to create a daily map, you have to understand how to combine them all. And you're going to have to read in all this data and its uncertainty information and try to work with it. The next image is, this is geostationary data. So this is data from a satellite that is about 35,000 kilometers from Earth. And it sits way back there and just takes a snapshot. The newer one's like a snapshot every 15 minutes of certain regions, and every 10 minutes, sorry, 5 minutes, and then every 10 minutes for the whole hemisphere. And again, you have data missing for clouds or other reasons. And you want to try and bring these all together into some sort of map that looks like this, that you can use for science, you can use for weather prediction. And this is what ideally you want to end up with after you bring all that different satellite data together. So the way it's done now, let me see, got a little stuck there. So the traditional pipeline, and this is where we start to talk about cloud computing and Dask and all of this. So traditional pipeline, download it, right? Okay, so that takes a long time because we have a lot of satellites. And then you filter it and debias the data. And you and I were talking about this before we got on the live stream, but a lot of the way that all of these products are produced now that I know of is there is a lot of pre-processing, which means we're breaking the data into bite-sized bits because we're still programming in Fortran. We have the memory that we have. We don't do lazy loading. And so it's all about taking the data and breaking it up into all these different bits that are just big enough that, or just small enough that you can fit them into your memory. And you're going to run your analyses over that data. And you may have up to, 8, 10, or 20 different processes running that are, bringing in the data for that small region, calculating the daily temperature, and then you have tracking files, and you have a main program that's controlling them. And this is a lot of code written by people who weren't supposed to be really writing code. Like myself, trying to keep track of this is really difficult, and it makes it very prone to failure and requires a lot of maintenance. And this is how most things are done now. The future pipeline, which I think everyone is going to move to in the next year or so, is stop downloading it, work on the cloud. You still have to do some of your data filtering, but this can all be done, with lazy loading in a delayed fashion. So you build your pipeline, you know what you need to do, and you just go straight to some sort of like Prefect managed interpolation analysis. And this is the advantage of using Dask here, is that you can have access to everything and then just run the interpolation, run your scheme at the very end using delayed. And this makes everything so much simpler because to me, Dask is like, it just manages all the memory. It manages all of the workers. It does all of that stuff that I used to have to do and write in my really kludgy Fortran and tracking files, it all sort of is very graceful in Dask. And that's a big advantage because my training consists of this. And so I really appreciate it when like software professionals do something really well that I can just take and use.
Absolutely.
And that's about it.
Fantastic. So firstly, and I said this before, I love that you have some Tim and Eric Cosmos magic here. That is one of the great classics. But I also like that the way you spoke about Dask, and also Prefect, which we're huge fans of here as well, is that they tend to abstract away a lot of the stuff that you don't necessarily, ideally, you wouldn't need to think about or need to do, and they do so gracefully. And I think that's key to allow you, as we've talked about before, to bring all of your skills to do the science that you want to do and need to do.
Yeah, you probably know this as well as I do, that every time you write a line of code, you risk writing a bug.
Yeah.
The less lines of code that I can write, the easier my code is to understand, the easier it is to collaborate with other people, and the less errors there are going to be.
Absolutely. I think that segues really nicely into executing some code together.
Okay, let's go.
Yeah. And for everyone on the live stream, I've shared from the Coiled account the notebook that Chelle will be using. I've shared it in the chat from Chelle's GitHub repository.
So this is a.
So we actually have one question from Tom Nicholas that I'd love your thoughts on. What is Prefect?
So you guys, I first learned about Prefect in a live stream. It's like the way that I think about it is it's a way of scheduling. It's a task scheduler, but you can pass data, you can pass programs. It's a way of building a pipeline that's a lot better than how I used to do it.
Exactly. So it's about essentially automating data flow and building those pipelines. So it's not Airflow. If you've heard of Airflow, that's something that some people use, but it's not Airflow. And it is very fundamentally, it helps you set up your data flow or automation and your, I suppose, data science pipelines and your data engineering pipelines. So definitely check out Prefect.
I think that's one of my favorite things about these live streams is learning about new software tools.
That's one of my favorite things about, like, I get to sit here and like listen and communicate with fantastic people doing really cool stuff. So much fun.
Yeah, so this is like a GitHub, right? So this is just a Jupyter notebook that I'm sharing. And what I did here is I developed it for a meeting called Ocean Hack Week. And it's a 1-week coding event that we hold every year. It's sponsored, it's held through the University of Washington. And we've been going remote. So if you're interested in coding with a bunch of oceanographers, it's all skill levels, and it's called Ocean Hack Week. And it's really fun, and we bring in lots of people, and we all work on some projects together. And so one of the tutorials that I sort of brought to Ocean Hack Week was talking about how to access some of the satellite data that's already on the cloud. And satellite data comes in 4 flavors. They're named level 1, 2, 3, and 4, which doesn't tell you a lot about what it actually is, but eventually you just sort of memorize it and then you understand. So level 1 is a satellite observation, and it's gridded-ish. It has a lat long and a time associated with each data point. And it's because it's usually from those polar orbiting satellites. And so it would be just an array of data that would show you which scan line that it was on and which cell position. Level 2 data is you take that data and you actually derive geophysical retrievals from it. So the ocean temperature or winds or whatever you're looking at, chlorophyll, still with long time associated with each data. Level 3 is mapped to a grid that's
And
uniform.
just quickly, where does so when you derive the geophysical retrievals, where does that computation happen?
Yeah, so this, usually there's an algorithm that goes between level 1 and level 2 that a science team has decided, okay, this is the algorithm that we're going to use to go from level 1 to level 2. Traditionally, those algorithms are proprietary and not shared. So for one SST algorithm, I think I started counting and I knew of 15 different independent funded efforts to derive the same geophysical variable, because nobody in the science community, open software still is just starting to take off. It hasn't been embraced yet. So think of what we could do if everybody just shared their code.
Yeah, I mean, I think I was going to say a satellite question. Forgive the poor pun, but a satellite question is how do we? I mean, we've used MATLAB for years as well, and that type of stuff. But how do we feel about doing quote unquote open science, which is derived from source code, which isn't open?
Yeah.
And there's an argument that open source software is technically open, but not practically open as well. Like it isn't like we dive into, you know, all the code bases of everything we use or even are able to, right?
Yeah.
But there's a community of people we can communicate with about it at least.
And I think that that's part of why federal agencies across the world are really pushing for open source software is traceability. And for most of the algorithms that I know of, you're required to describe your algorithm and sometimes provide the code to an agency, but it's not shared openly. And what that means, there's two problems with that. And one is traceability. And two is just redundant efforts left and right and all around you, because the code to go from level 1 to level 2, 90% of that code everyone is writing and it's the same because it's the IO and you're just trying to get the data in, read it in accurately, do a couple things to it, and then output it accurately. And all of the stuff in between, you know, the equation that goes in a couple lines of code is redundant in all these different efforts. And the way that you filter the data, it would be really nice to share that so that everyone else can benefit from it. So I think earth science is moving towards that direction, and there's a lot of momentum behind that. It's just stuff that's happening right now.
Yeah, takes time.
Yeah, it takes time. And, you know, it takes time for a reason, right? There's people who've developed their funding cycles and a lot of things depend on these. So you don't want to cause too much change in science. You want it to move forward, but every time you change something, it's going to set it back a little bit. So you have to be a little bit careful about how you try to make change.
I agree. I do think there's, so as you may remember, I used to work in biophysics and cell biology.
Yeah.
And even 10 years ago, a lot of people were using MATLAB, and there's been a huge shift into people using open source software now, whether it be Python in a lot of sciences or R as well. And of course, after that, things to open up the space, things do take time. I do, and this may be going down a rabbit hole we don't want to go down too far, but I do think we're in one of the first times in at least recent history in past 100 years where, let me be clear, a lot of the scientists, a lot of the people in power are boomers. And I think we are at a time where a lot of people in positions of power in tertiary education institutions and in research are significantly older on average than they have been previously. And there is some sort of gatekeeperism around the tools and techniques and openness used, if that makes sense. At least in my experience.
Yeah.
I can't speak for your field and wouldn't want you to, you know, jeopardize it.
I'll just wink if I agree.
Yeah, sure, great.
Yeah, I think that gatekeeping is problematic in that, and you know that one of the areas that I work in is one of the reasons it's hard to share a level 1 to level 2 algorithm, a geophysical algorithm, is because it's designed to run on some scientists or some agencies' very specific computational environment. Mm. It's designed to run with a very specific compiler and in a structure and environment that is hard to reproduce. And Jupyter and having Jupyter hubs and Binder and all of that whole ecosystem is changing, like Python and being able to install Conda environment files where I can replicate exactly, you know, I have environment files that replicate supercomputer environments and other ones that for me to work on. And that makes it so easy to actually share how someone is working on something. And so as these algorithms move to Python, a lot of the reasons that they weren't shared before disappear. And when you provide that access to your environment that can be run locally or on the cloud, you're opening the door outside of these institutions and these agencies to any scientists anywhere in the world to do science. They don't need to download big data sets. They don't need to have a big supercomputer. All they need is a cell phone that they can connect to, you know, AWS or Google Cloud product and start a process. And if they know they're going to lose power in a half an hour, that's fine. They can start it and then come back to it.
Yep.
And that's game changing to me. I mean, having different voices being able to participate in science is really going to change for the better what solutions we find.
You just reminded me, I actually, several years ago when I was flying to Austin for SciPy to teach a workshop, and I'd messed up something in our repository, and I'd pushed it to master, and I was on the plane and I realized this, and I was like, oh, holy, insert expletive here. And I got on my cell phone and launched a Binder repository and executed all the code as my, you know, United flight took off, and it all executed well. There were a few typos, but I was like, oh, okay, great. And I could enjoy the rest of the flight knowing that was fine. So
yeah, and like you couldn't have done that 5 or 10 years ago, right?
No, not at all.
I got my kids these Raspberry Pis. Have you played around with those?
Yeah, I have, but I remember you. Yeah, that's awesome.
And so like I installed the open source Kano operating system, which is more geared towards sort of the 8 to 12-year-old age. It has lots of games for Python, but it also has, you know, a browser. And so on the browser, like I'm working a $36 computer, and I'm in a browser connected to AWS in one window and Google in the other window. And I have like, you know, 60 workers and 300 gigabytes of data processing on this little tiny computer I built, which is so cool.
It's crazy, isn't it?
Yeah.
All right, let's jump into the data.
So in the tutorial, I sort of talk about how to find the data on the cloud. So there's this registry of open data, and this in particular is on AWS that I'm working on right now, but Google Cloud, Microsoft, all the big cloud providers have similar open data programs. And when it's open data, it normally means, not for every case, but most of the cases, it means that you can access the data for free. You're still going to pay to do computation, or you can just access it from your local computer, but accessing the data is free. And often it's hosted in a cloud optimized format that makes accessing it even easier. So this is a 1 kilometer global temperature data set. And this is put into a Zarr format. So first, I'm just gonna run this cell, and it's just, you know, doing the usual imports. Some of my favorite libraries like S3FS and FSPEC and Xarray, of course, I have to point out and give credit. Now we're going to access, so this is like a 4 terabyte data set, I think. And we're accessing it in its S3 bucket just as a call. We're creating a mapping to that location, and then we're using X-ray to put it into a DS-SST, which is an X-ray data set, and then we're displaying it. So in 12 seconds, we've essentially loaded all the metadata only. We haven't really touched much of the data yet. And I love this because you can see all of the metadata, so you understand what you're looking at, who produced it. It tells you the different data variables that are there, what their dimensions are, what type of arrays they are. And then here, there's the Dask array, and this is the chunk size. So for this Zarr data set, there's actually 2 mirror data sets on AWS. One is chunked. So this is the time, lat, and long. So this is one big chunk and time. And then there's another one that's chunked more evenly through time and space. So the chunking becomes really important depending on what type of analysis you're doing. If you're doing time series analysis, having one chunk in time is really advantageous. So here we're going to read 10 years of data at one point. So simply being able to read the data, we already saved like 1 week of downloading this data set by just accessing it on the cloud. And it took 2 seconds to go through that and plot 10 years of data.
Awesome. And so if you scroll up, what SST time series is, what type of object is that?
This is a X-ray data set. So these are data arrays. Yeah,
great.
Still an X-ray.
This may be obvious and a bit low level for a lot of people, but I just want to say how much like of the open source ecosystem has gone into producing this plot, for example. I mean, we actually, we have X-array, and then we have a plot method, which is calling matplotlib, which is then rendered in a Jupyter notebook, right? Within Jupyter Lab. And this interoperability of all these tools and technologies allows you with great ease to produce a figure like this, right?
Yeah, and before, I mean, even being able to read the data set in a couple lines, I mean, this is reading a data set that originally consists of like, 8,000 files. And if I had started in Fortran, the first thing would be to go through each and every single file, open it, and access just the data point that I wanted. And that would have taken a lot longer than 2 seconds.
Yeah.
And the code would have been really complicated because I would have the code to create the file name, I would have the code to read it in, to save it into an array, and then to come down, output the data, and then move to MATLAB or another program to plot the data. And you're right, here they're all integrated. And the other thing that I really love and appreciate about X-Array is when you want to select data. So you use cell, and like, you can probably look at this command and you can say, well, what is she doing? She's selecting a time slice of 10 years at this latitude, at this longitude, and then I'm plotting the data. And being able to read the code like that, to me, is really easy because you're not operating at indices, you're actually operating in the coordinates. And that makes it a lot less easy. I've made a lot of indice mistakes in my lifetime.
Yeah, I can relate to that.
Is it zero based? Is it one based? Is it going up or down? Did I so.
And so it looks like we have one latitude, longitude, so 1 point on the globe over 10 years, and we see seasonality, among other things, emerge.
Yep. Yeah, so you're seeing a seasonal cycle. You see variability, and you see that seasonal cycle, the amplitudes increasing and decreasing through different years. And I happen to pick a particular point.
Where is it?
It's in the minus 145.47. So it's up in the sort of Pacific blob region.
Okay.
And if we wanted to look at the anomaly, so like, let's see, is it warmer or cooler than normal? And that's something that's really common. So this is going to take almost no time to do. I was going to say this is going to take a while. It took less than 1 second. Wow. So what we've done here is I've grouped it by day of year. and then I've taken the mean in time. And so that creates a climatology. I then took the anomaly by grouping again by day of year and subtracting the climatology. So that removed that annual cycle. And then I resampled it to a monthly, and I took the mean over a month just to take out some of the noise. And then again, I'm just plotting it. So, take this and plot, and draw a line at 0. So the blue data is the original data set. And this is the anomaly that shows how much warmer it's been getting in the Pacific. And the orange line is the monthly data set, where now I've just taken out some of the noise to make it a little bit smoother.
Great. So we have a couple of questions from the crowd. Guy Maskell is asking, Chelle, this notebook we're looking at, is it running on Pangeo on AWS in US Central 1? So the only thing you're running locally is the browser?
Yeah, so this, I think I was just being lazy because I was already I was doing some stuff with wind speed. So I already had Pangeo open. So I'm running on Google Cloud. Okay. And it's running in US Central 1, and it's the Pangeo platform that I'm running on. This particular notebook will run locally. It'll be a little bit slower, or it will run on either Google or AWS equally well.
Great. And we have 2 questions from Tom. The first is, how long did it take, or how hard did you find it to turn the original netCDF data into Zarr?
Since we have this code open, I think, okay, I realize my it's all a mess. So don't judge me on my organization. Again, I took no software training. I want to say that if I go down,
I also worked with biologists for years, so.
There you go. Okay. Yeah. I think it might be in something similar is going to be in here. No, so this is just a similar notebook. This going to Zarr for this big data set, I worked with Development Seed, Amy Barsoskas, to do this, and she and I worked together to do it. So it took a while. It took a couple weeks. The one example I know I can show you, which is a little bit smaller, is, and I think it's actually worth showing because it's really interesting to make the Zarr files. So CCMP is a wind data set. It's about 300 gigabytes. It's from 1988 through present 4 times a day. And to create the single Zarr store for that, and it's better to create a single Zarr store because it just consolidates all the metadata. And because you're always doing lazy loading, it just makes everything simpler. So you don't need to break up Zarr files like you used to with netCDF. So I create some patterns to read in the files. Here's where I read in all of the global files. I read it using OpenMF dataset. I just make sure there's no repeat because there's some real-time files mixed in with the data. So I remove any duplicates. I set my chunk size, and then I say to Zarr. And I think this notebook runs in maybe 45 minutes. And most of it is, the only reason it's, it just has to create a 300 gigabyte data set on my drive. So actually creating a Zarr store, you want to be a little careful and thoughtful about how you do it. But once you get the code running, it's as simple as one line. And again, This is because of a lot of work that the Pangeo group has specifically done with Zarr. And it makes it really easy to access these big data sets. So this, awesome. Because it was huge, I mean, it was just a truly huge data set, took working with the software developer, Amy, and it took a while. But, when you're not talking about 4 terabytes, it's a lot easier. So 300 gigabytes is pretty easy.
So
And if
we have
you
around
want,
10.
you can message me and I'll send you that code. It's in my GitHub Cloud Science Make Zarr. I have a bunch of different examples for data sets that I've created Zarr stores for.
Great. So we've got around 10 minutes left. We can go a bit over, but I just wanted to state that so we know how much we can get through.
Yeah. So if we wanted to look at this is just another. This is an interesting. I like plotting this one. So I went into the Chukchi Sea up in the Arctic, and what you see is actually there's these flat periods. So that's when it's ice covered. And so one of the things is sometimes it's so easy to get this data now, you forget that you need to do a lot of understanding. Like it's really, please read the metadata and just plot and map the data in a million different ways so that you understand, you don't want to just take a mean of this data because you'll be including all this area that's not mass, that's actually just ice covered. And there's an ice mask in the data set that you can apply, and you just have to know to look for it. And so when you get data, especially on the cloud where it's really easy to get access, it's the first time you use it, it's worth spending some time understanding that data set. Let's see what we're doing here. So here we're gonna plot some different subsets of the data from different days. And this is another example of why understanding the data is important. So the 1 kilometer data set actually blends data from a bunch of different satellites. And those satellites have different resolutions. And sometimes when the high resolution data isn't available, you still get data, but it will look more like this. Versus when the higher resolution data, this is the same reason, just on a different day that wasn't so cloudy. So a lot of the high resolution data was available. And as that image comes up, you'll see like there's a lot more what we call sub-mesoscale, but small scale variability in the ocean that you just don't see when we have lower resolution data going into the analysis. So just because something's gridded at a certain grid resolution doesn't necessarily mean that it's always that spatial resolution.
That's fascinating. I'm interested in two things. I want to know how to find an AWS public data set, absolutely. But the other thing that I find fascinating, we've chatted about this before, is that it almost looks like you haven't used Dask at all.
So you and I talked about this. I love Dask because it just makes doing my science this. I don't have to worry. I think that we're entering this period of transformational science where scientists are really going to be empowered to do science, and they can do science quickly and fastly because they no longer have to be fairly sophisticated software developers. And the reason that I can write in one code what I want to do and how I want to image it and how I want to do this analysis is because behind Xarray, there's Dask figuring out how to do everything for me. And especially, I think that is much more apparent in the call where I'm doing where I'm grouping things together and taking means and doing a fair bit of analysis to create an anomaly. Before I would have had to go through the data set, create my climatology, save that, output it. And then I would go through the data set again and subtract that climatology from it. But Dask is essentially, at least the way that I see Dask interacting with Xarray, is that it's worrying about how the data is chunked. It's only getting the data that it needs. So it makes it so that I can run this on a reasonably sized computer and not worry so much about memory constraints.
That's great. And it actually, I think diehard fans of our Science Thursdays will have heard me say this before, but I think it's worth repeating. This speaks to a really interesting point of some of the design principles of Dask that go back to the first lines of code that Matt wrote when he was working on kind of the ideas behind Dask with people at Continuum and Analytics and Anaconda. There were technical goals, but there was also a social goal. And the way Matt frames that is the social goal of Dask was to invent nothing. And what he really meant by that was to meet people where they are, so that everything Dask did was abstracted away. So you didn't necessarily need to figure out what was happening, to work with Dask to recognize what it was doing all the time.
Yeah, and you and I have talked about this before, but that's something that attracted me to Xarray was the incorporation of Dask initially, because all of my coding from the very first time that I had a research job, it started with, okay, here's a file, here's how to read it, this is what array shape is, and this is how much data you can read, and this is the data. And I always had to think about the data. And because I learned how to do science when the first step was thinking about the data, I think that my mind is in some ways limited to what problems I think I can answer and what questions I think I can ask. Because in the back of my mind, I always know too much about the data constraints. And I feel like we're going to enter a period fairly quickly where there's going to be a generation of scientists who don't worry about that because they don't have to. And that's going to change what possible questions they're asking. And I'll try to change and adapt with them. But, you know, it's just fundamentally different. You don't say, well, okay, how do I create a climatology? You just say, I want a climatology.
Yeah.
And it changes how you do science.
And I do think, I don't know if we've touched on this explicitly before, but something I think about a lot and talk about a lot is how one of the reasons Python has garnered such large adoption in the data space in research and industry is that a lot of the packages aren't built by classic software engineers. They're built by scientists trying to solve problems, right?
Yeah.
And tinkerers and hackers, right? Which I think is key.
And like Xarray and, you know, in astrophysics, there's AstroPy, and it's scientists getting involved and then starting to build something, and then software developers recognizing a problem and everybody starting to work together. And then suddenly there's this tool that is useful to, you know, a huge percentage of the community, so that people don't have to write their own darn code again and again and again and again, exactly, and then email it around to each other. Yeah, we were just talking about GitHub the other day and how I used to share code over email, and then if you changed anything, you would have to go through your email and try to find who you had shared the code with so that you could.
Yeah, exactly. So we'll wrap up in a minute, but maybe you can tell us, I think it'd be nice to wrap up on how to find these data sets and kind of next steps for people interested in exploring them.
Yeah, I think that because this was a short tutorial, I only really talk about AWS here. And I apologize to anybody interested in Google data sets, but you can Google, you know, you can Google open data programs. And a lot of the data sets are on both open data programs or Microsoft as well. I don't want to leave them out because they've been very active in this area as well. But if you go to, within the notebook, there's some clicks that launch you to the open data program on AWS. And it starts to give you some introduction to different data sets. And all of the different, they have everything from biology to life sciences. You know, this has been transformative for COVID research as well. And I sort of, in the Jupyter Lab, I also talk about how to find the different data sets, and then I give some examples of how to navigate it. Because when I first went to the open data set program, both on Google and AWS,
Great. And I encourage anyone who's interested in pursuing it further to go through the rest of the notebook and let us know how you go. We have one final question from Eli or Ellie Kling. Eli asks, Eli has a concern around future-proofing, especially with the advent of a lot of new libraries. So Eli worries about using new libraries. Are they robust? Will they be maintained? How can we be? Yeah, I suppose that's the question. What are your thoughts on that, Chelle?
Yeah, so software libraries are, you know, that's one of the complaints I think that people have about Python, is that there's lots of updates. It's hard to keep track of everything. You could have broken code. I think that one thing that's really important is to maintain an environment file that has versioning for the different libraries that you use, so that your code is will always run. As long as you put that version, so if you don't know what an environment file is, you can probably Google that, and it's basically a file that lists all of the different Python libraries you're using, and you can put versions in there as well, so that that environment is static, you know, it's unchanging, and you know that code developed there will always run. You can circumvent some of the uncertainty with newer libraries by doing that, because then it doesn't matter how old or new they are and how much they're changing. But it's really important when you start using a Python library to explore whether that's the best library, whether that's, how popular is it, how many people are using it. Generally you want to try and use libraries that are well developed, that have an active community, and you can, you know, explore that on GitHub. You can see how many people are contributing to it. I mean, how do you assess that, Hugo?
It depends what you're doing. I think if you're working for, okay, when working in industry and putting stuff into production, you do, I mean, whenever you start using new software, you take on a certain amount of risk, and you probably need to quantify that, particularly if you're putting things in production immediately, and identify the costs associated with things that aren't necessarily developed. So I encourage people to think in terms of maturity of projects. So, you know, would I be fine putting Pandas in production? Most certainly. But newer projects, you really do need to identify and quantify the risk, I think.
Yeah, and I like, this is one way to do it, right? You go to the GitHub for a library that you're interested in. How many open issues are there? How many pull requests? Who's working on it? How many people are, you know, working on this library? Is it active? Has the last update, you know, 6 years ago and it's dead? Or is it, you know, really recent? So this was, you know, the last one was released February 25th. There's been 59 releases. And it's important, if you're going to be using Python, learning how to evaluate what libraries you want to use is an important part of it.
Absolutely. Guy Maskell cheekily says, using new libraries usually beats having to keep using the old libraries, which I generally agree with. So look, this has been fascinating, Chelle. Thank you once again for sharing your work with us, and sharing your time as well. We said as next steps, people, please, if you want to explore more, feel free to go through the notebooks. And if you're interested as well, check out Coiled Cloud, where we have, among other things, one-click hosted deployments of Dask clusters that allow you to scale your data science work to the cloud immediately without all the, you know, taking the DevOps out of data science, as we say. But Chelle, are there any other next steps if people wanted to dive in and learn more about this stuff?
I think that if you're in earth science, or if you're Pangeo is a great open science community, to reach out to. I think Twitter science, like following different groups like Coiled on Twitter. I mean, that's really how often I learn about new libraries. And you see somebody do something cool on Twitter, they post something and then they post the code and you learn about cool new libraries to use or ways to do things. So I think those are really good ways to interact with the community. And now that we're all remote, people seem pretty active online. So
yeah. And I was talking with a few people about this yesterday. I started a Twitter account in 2012 or something like that, and maybe a bit later, and just wasn't active until I started working more in data science. And essentially when I started really working community building in data science, and it became clear that Twitter was such a space for exploration there firstly to meet and interact with people who are interested in similar things, but in a space that's I think moving so quickly, and in which there's such a kind of interestingly fragmented yet also connected network of tools and techniques and skills that moves so quickly. Twitter just happens to be a great place to stay updated and keep in the loop.
Yeah, and
for whatever reason.
When I was first learning Python, like I didn't know how to ask questions. And Stack Overflow, every time I posted a question, like I think I wasn't ever asking it in the right way, and so it would never get answered. And Twitter, because it seems to be such an active community, like people post coding questions on it a lot, and they have answers almost immediately. And it's really fun. Like I really like that part of Twitter. Sometimes somebody says, go to Stack Overflow, but I actually really like it on Twitter.
Me too. I like how you say, I like that part of Twitter, because there are parts of Twitter which are eminently unlikable.
I don't go there.
Great. Well, thank you once again, Chelle. And everyone out there, if you enjoyed this, hit subscribe. You can communicate with us on Twitter and through other channels if you have any further questions. We have more live streams and webinars coming up, so definitely follow us. So thank you once again, Chelle.
Take care.